fill the sky in every direction with a faint, uniform glow of microwaves, and you have before you the oldest light in the universe. The cosmic microwave background, a near-perfect thermal radiation at a temperature of just 2.7 degrees above absolute zero. It was released when the cosmos was some 380,000 years old. At the moment, the hot primordial plasma cooled enough for the first atoms to form, and the fog of the young universe finally cleared. That ancient light has travelled, stretched and cooled by the expansion of space, for nearly 14 billion years to reach us. Predicted as the relic of a hot beginning, and then stumbled upon by accident, it has become cosmology's single richest source of knowledge, a photograph of the infant universe from which we have read its age, its composition, its geometry, and its history to a precision that would have seemed impossible only a generation ago. This chapter is the story of that light. To understand where it came from, picture the universe in its first hundreds of thousands of years. A hot, dense plasma of photons, free electrons, bare protons and helium nuclei, all bathed in a sea of dark matter. In that plasma the photons could not travel freely, for they scattered incessantly off the free electrons, and the whole photon-electron-baryon system behaved as a single glowing fluid held in thermal equilibrium. Because matter and radiation were locked together at a common temperature, the radiation took on the characteristic spectrum of a perfect thermal emitter, a blackbody. As the universe expanded, this fireball cooled, its temperature falling in exact step with the stretching of space. And so long as it stayed hotter than a few thousand degrees, any neutral atom that tried to form was instantly shattered by the surrounding bath of energetic photons, keeping the electrons free and the universe opaque, a wall of fog through which no light could pass. That such a relic glow should still fill the sky was foreseen remarkably before it was found. In 1948, George Gamow and his colleagues, working out how the light elements formed in a hot expanding universe, estimated that a relic radiation of a few degrees above absolute zero should survive to the present. The prediction was forgotten for nearly 2 decades, until a group at Princeton reasoned their way to the same conclusion and began building an antenna to hunt for it. They were beaten to it by accident. In 1965, 2 radio astronomers at Bell Laboratories, Penzias and Wilson, were struggling with a persistent, uniform hiss in their horn-shaped antenna that came from every direction and would not go away. They checked every source of error, and even evicted a pair of nesting pigeons and scrubbed out their droppings, the white dielectric material, before concluding the signal was real. It was the background itself, and it would win them the Nobel Prize. The light was set free at the epoch cosmologists call recombination, the moment the electrons and protons first combined into neutral hydrogen. As the radiation cooled to around 3,000 degrees, at a redshift near 1100, the photons could no longer keep hydrogen torn apart, and the free electrons were swiftly captured into atoms. With the electrons gone, the photons had nothing left to scatter from, and their mean free path exploded from almost nothing to the size of the observable universe. In that instant, the fog lifted, the universe became transparent, and the radiation streamed freely outward to travel undisturbed ever after. Because this happened everywhere at once, we today see the light arriving from a vast spherical shell surrounding us, the surface of last scattering. It is, in a precise sense, the universe's photosphere. Just as we cannot see into the opaque interior of the sun, but only its glowing surface, so we cannot see beyond this cosmic surface, frozen at an age of 380,000 years. The defining property of this radiation is that its spectrum is an almost flawless blackbody, the exact thermal curve first described by Planck. This is no accident, for a blackbody spectrum has a beautiful property. As the universe expands, it remains a blackbody, the redshift merely sliding its temperature downward while preserving the perfect thermal shape. So the spectrum imprinted in the hot early plasma survives to today, cooled but undistorted. Its perfection was established by one of the most exacting measurements in the history of science. In 1990, an instrument aboard NASA COBE satellite compared the sky against an onboard reference furnace of precisely known temperature, and found the cosmic spectrum to match a blackbody to within 50 parts in a million, the most perfect thermal spectrum ever measured in nature, at a temperature of 2.725 degrees. No process other than thermal equilibrium in a hot, dense, expanding plasma is known to produce such a spectrum, and it stands as the spectral cornerstone of the hot Big Bang. Perfect as it is, the background is not perfectly uniform, and its tiny departures from smoothness are where its real treasure lies. The largest is the dipole, The whole sky is very slightly hotter in one direction and cooler in the opposite one, by about 0.03 of a degree. This is not cosmological but a mark of our own motion, the Doppler shift produced as our solar system sweeps through the radiation at some 370 kilometers per second, the combined drift of the Sun through the galaxy through its local group, and the local group toward distant concentrations of mass. Subtract that dipole and the residual variations are extraordinarily faint, fluctuations of just 1 part in 100,000, a few 100,000ths of a degree, from place to place across the sky. Yet these whispers are the cosmologically precious signal, the imprint of the small density ripples in the primordial plasma, the very seeds that gravity would amplify over billions of years into galaxies, clusters, and the entire cosmic web. To extract the information in those fluctuations, cosmologists do not study the map point by point, but break it down into patterns of different angular sizes, much as a sound can be decomposed into its constituent tones. The result is the angular power spectrum, a curve showing how much fluctuation there is at each scale, from the broadest features spanning the sky down to the finest ripples. Large angular scales sit at one end, small scales at the other, and the shape of this curve is the central observable of the whole subject. But there is a fundamental limit built into it. On the largest scales there are only a handful of independent patches of sky to measure, so no matter how good the instrument, the curve there is irreducibly uncertain. We have, after all, only one universe and one sky to observe. This unavoidable haziness on the largest scales, known as cosmic variance, is one reason the puzzling anomalies at those scales are so hard to judge. The power spectrum is far from featureless. It rises and falls in a series of harmonic peaks, the acoustic peaks, and their origin is one of the most beautiful stories in cosmology. Before recombination, the plasma rang like a struck bell. Gravity, led by the dark matter, pulled the photon-baryon fluid into dense clumps, the photons' radiation pressure pushed back out, and the tug-of-war between them set up standing sound waves rippling through the plasma. Every ripple of a given size oscillated between compression and rarefaction, and then, at the instant of recombination, the photons were suddenly released and the oscillations froze in place. Ripples caught at maximum compression or maximum rarefaction left the strongest temperature imprint, those caught mid-swing left the least. The result was a harmonic series, a fundamental tone and its overtones written across the sky, a frozen chord from the music of the infant universe, and each peak in it carries a distinct piece of cosmic information. The first and tallest peak is the most eloquent of all, for it serves as a cosmic standard ruler. Its physical size is fixed by known physics, the distance a sound wave could travel in the plasma before recombination, about 140 megaparsecs. Knowing the true size of that ruler and measuring the angle it subtends on the sky, we can read off the geometry of the space the light has crossed to reach us. In a flat universe, the first peak should fall at an angular scale of about 1 degree. In a positively curved closed universe, the angle would be larger, and in an open one smaller. The measurement is decisive. The first peak sits almost exactly where a flat universe demands, and Planck has pinned the acoustic scale to a precision of 3 parts in 10,000. The verdict is that space is, to within tiny measurement errors, geometrically flat, one of the cleanest and most important results in all of cosmology. The other peaks tell their own tales. The plasma's oscillations alternated between compressions and rarefactions, and the odd-numbered peaks correspond to the compressions, the even ones to the rarefactions. Because the baryons add weight and inertia to the fluid, they deepen the compressions relative to the rarefactions, so the relative heights of the odd and even peaks weigh the density of ordinary matter in the universe. The third and higher peaks, in turn, are sensitive to the amount of dark matter, and at the smallest scales the peaks fade away into a smooth decline called the damping tail. Because recombination was not instantaneous, photons had time to random walk out of the smallest clumps and wash them out, a blurring known as silk damping. Reading the whole pattern of peak positions and heights, then, is like reading a detailed inventory of the young universe's contents, and the measured spectrum matches the theoretical prediction with breathtaking fidelity. There is more information still, for the background is not only varied in temperature but faintly polarized, its light waves slightly aligned. This polarization arises because an electron scattering radiation that is hotter from one pair of directions and cooler from the perpendicular pair emits light with a net polarization. The flowing, oscillating plasma at last scattering created exactly such patterns. The polarization is decomposed into two geometric types. The so-called E-modes with a smooth gradient-like pattern are produced by the same density oscillations that make the temperature peaks, and their detection has richly confirmed the whole acoustic picture. The other type, the curl-like B-modes, cannot be made by density variations at all. They arise from only two sources: the gravitational bending of E-modes by intervening matter, now routinely seen, and most tantalizingly, primordial gravitational waves rippling through space from the epoch of inflation itself. A detection of those primordial B-modes on large angular scales would be a near-direct fingerprint of cosmic inflation, the hypothesized burst of exponential expansion in the universe's first fraction of a second, which generically shakes spacetime and sends out a background of gravitational waves. Their strength is measured by a quantity called the tensor-to-scalar ratio, and no primordial signal has yet been found. The tightest limit from an experiment at the South Pole has driven that ratio below a few hundredths, ruling out the simplest inflationary models. The hunt carries a cautionary tale. In 2014, one team announced a detection, only for it to emerge that the signal was polarized dust in our own galaxy masquerading as the cosmic one, a chastening reminder of how delicate these measurements are. Inflation remains a well-motivated and successful framework, elegantly explaining the flatness and the fluctuations the background reveals, but its defining prediction is still unconfirmed, and it must be held as a hypothesis, not a fact. Almost everything we know of the background comes from 3 satellites, each a generational leap over the last. COBE, launched in 1989, established the blackbody spectrum and made the first detection of the faint anisotropies, its team announcing in 1992 the discovery of the primordial ripples, a result Stephen Hawking called with pardonable exaggeration the discovery of the century, and winning its leaders a Nobel Prize. But COBE vision was blurry, its beams smearing over 7 degrees of sky, too coarse to see the acoustic peaks. WMAP, launched in 2001 to a vantage point far beyond the Moon, sharpened the view to a fraction of a degree, resolved the first peaks, and fixed the age of the universe near 13.8 billion years. Then Planck, launched in 2009, mapped the sky in 9 frequencies at a resolution of 5 arcminutes, capturing the full sweep of the acoustic series out to the finest ripples and the damping tail, and delivering the definitive measurements on which modern cosmology rests. The great payoff of all this precision is that the shape of the power spectrum, fitted to the physics of the plasma, pins down the entire contents and geometry of the universe. The standard model that emerges is astonishingly economical, a flat universe described by just 6 numbers. From these 6 parameters, the density of ordinary matter, the density of dark matter, the scale of the sound horizon, a measure of when the first stars re-ionize the gas, and the amplitude and tilt of the primordial ripples, everything else follows. It is a remarkable compression, thousands of independent measurements across the whole power spectrum, all captured by 6 adjustable quantities. That a single 6-parameter model should fit so vast a body of data, and fit it so exquisitely well, is the strongest quantitative success in all of cosmology, and the foundation on which the modern picture of the universe is built. Each of those numbers is read from a specific feature of the spectrum with real physical transparency. The angular position of the first peak fixes the geometry and reads flat. The ratio of the odd to the even peak heights fixes the density of ordinary atomic matter, and in a striking confirmation, the value it gives agrees precisely with the completely independent figure from Big Bang nucleosynthesis, 2 utterly different probes of the young universe converging on the same answer. The overall heights fix the dark matter density, and the gentle tilt of the spectrum across scales gives the character of the primordial ripples. The background finds that they were very nearly but not exactly the same on all scales, slightly stronger on larger scales, a subtle redness that is just what inflation predicts, since an inflationary epoch must end and so cannot produce a perfectly uniform spectrum. Assemble these numbers and the universe they describe is the now famous concordance model. Space is flat, its age is 13.8 billion years, and its present contents divide into 3 strikingly unequal parts. Only about 5% is the ordinary atomic matter of stars, planets and people. Some 27% is cold dark matter, unseen and unidentified, and the remaining 68% is dark energy, the mysterious agent driving the expansion to accelerate. What gives this inventory its authority is that it does not stand alone. the values drawn from the background agree within their errors, with entirely independent measurements from exploding stars, from the clustering of galaxies, and from gravitational lensing. A single coherent picture, derived from a faint microwave glow and confirmed from a dozen directions, describes the whole universe, the most precise and best tested account of the cosmos that science has ever possessed. The background is not quite a pristine snapshot, for its light has travelled through nearly 14 billion years of evolving structure on its way to us, and that journey leaves secondary marks that are both nuisance and treasure. As the photons cross the great webs of matter, their paths are gently bent by gravity, subtly distorting the pattern and smoothing the peaks. A lensing effect that, once measured, maps the total distribution of matter across cosmic time and even helps weigh the ghostly neutrinos. When the photons pass through the hot gas of a galaxy cluster, they are nudged in energy by collisions with fast electrons, imprinting a characteristic signature that lets surveys find distant clusters by their shadow on the background. And the slow decay of gravitational wells in a dark energy-dominated universe leaves its own faint, large-scale imprint, an independent line of evidence for dark energy written across the oldest light. Before any of this cosmological signal can be read, though, a great obstacle must be removed: our own galaxy, which glows in microwaves from spinning dust grains, from electrons spiraling in magnetic fields, and from the warm interstellar medium. These foregrounds are often brighter than the cosmic signal itself, and the way to defeat them is to observe at many different frequencies, for the galaxy's glow and the cosmic blackbody vary with frequency in different ways. This is precisely why Planck mapped the sky in 9 separate bands. With enough colors, the foregrounds can be modeled and stripped away to reveal the background beneath, and it was exactly this multi-frequency power that unmasked the false signal of 2014 as galactic dust. The same free electrons matter again, at late times, for when the first stars reionized the gas of the universe, they rescattered a small fraction of the background light, leaving a subtle imprint that tells us the cosmic dawn arrived when the universe was a few 100 million years old. For all its triumphs, the standard model anchored by the background is shadowed by genuine puzzles, and the sharpest is the Hubble tension. The present expansion rate inferred from the background, assuming the standard model, comes to about 67.5 kilometers per second per megaparsec. But measured directly and locally, by climbing the cosmic distance ladder from nearby stars to supernova, it comes out distinctly higher, near 73, and the two disagree at a confidence of roughly 5 sigma, far beyond what chance allows. The obvious escape, a hidden flaw in the local measurements, has been hunted hard and, with the James Webb Telescope confirming the key stellar calibrations, largely closed off. It matters that the background's value is not a direct measurement, but an inference from the model, which is exactly why the tension is so pointed. It may signal an unrecognized error, or it may be the first crack in the standard model, hinting at new physics in the early universe. It remains genuinely unresolved. Other puzzles are milder but real. There is a gentler tension over how strongly matter clumps between the background's prediction and some surveys of cosmic structure. There are a handful of curious anomalies on the largest angular scales: a strangely quiet broadest pattern, an odd alignment dubbed the axis of evil, an unexpectedly large cold spot, though because these were noticed after the fact and sit at the level where cosmic variance reigns, most cosmologists regard them as likely flukes rather than new physics. And beneath it all lies the deepest ignorance of all. The background measures with exquisite precision how much dark matter and dark energy the universe contains, yet tells us almost nothing about what either of them actually is. The next generation of instruments, new observatories on the ground and a proposed satellite, will chase the inflationary B-modes, weigh the neutrinos and probe the faintest distortions of the blackbody, hunting for the clues these puzzles demand. 6 decades after Penzias and Wilson could not rid their antenna of its stubborn hiss, the cosmic microwave background remains the most information-rich observation in all of science. From a faint, cold glow of microwaves, light that set out across the universe when it was 1,000th of its present age, we have reconstructed the geometry of space, the inventory of matter and energy, the age of the cosmos, and the very seeds of every galaxy, and we have tested that reconstruction against a dozen independent lines of evidence and found it whole. And yet the same faint light still guards unanswered questions about the expansion rate, about the nature of the dark sector, about whether inflation truly happened, that may yet overturn or deepen the picture it has given us. It is at once cosmology's firmest foundation and its most promising frontier, the oldest light in the universe, still, after all this time, the brightest guide we have to its beginning.